genome sequences of many organisms. And a new field of epigenetics has occurred, which is epigenomics, which is a mixture of genomics and epigenetics, that can easily understand. And now we can, I will go very quickly on the chemical aspects of it, because it's not very fascinating, but we have access now on a couple of model plants, which are rice and of course, Arabidopsis, on three major epigenetic modification, which are histone modification, acetylation, methylation, etc., DNA methylation, and small RNAs, which are really the three overlapping events which are governing epigenetics. And these changes can be accessed and mapped on the whole genome now. And this is confirming what we have discovered on a couple of genes. Now it's really amenable to genome-wide approach. So, yeah, it's changing a lot of things in the organization of laboratories and the organization of research groups, because we have now the center of everything, and we probably discuss about that tonight. Wow, that is right. Yeah, it's a dialogue between three different approaches: DNA methylation, chromatin, and gene expression. And all these activities are connected with a huge bioinformatics activity. And of course, these epigenomics database are connected to genome database. So I will just give you a few examples on a few model plants, which are a bit far away of what we are doing at the moment on farms, because the resources, this database on genome and epigenome are very scarce, but we can dream and think about it in the future. So what happens for example, on Arabidopsis? You can see here the correlation between DNA methylation, methylation of histone tails, presence of genes, and activity of transcription on the chromosome base. All these activities can be correlated on a genome-wide basis. And this is on a gene-rich region, and this is on a repeat gene region, which you can see that DNA methylation is much higher. And of course, the density of repeats is much higher on a heterochromatin zone. The same on if you look at the repartition of gene on one chromosome, and if you separate green chromatin and chromatin parts, you can see that the gene density is decreasing, and together with the methylation of histones, the intensity of DNA methylation, and the density of small RNAs, and of course the density of repeats, which are blocking gene expression. So this is really amazing, because for the first time in this paper in 2008, we can really see on the whole genome basis what we were thinking about on a single gene study, that now we really have the correlation between different epigenetic marks along the genome. Of course, and then after that, on the top of that, the small RNA world, which has been discovered quite recently, is another way of epigenetic regulation, which is really correlated with the former one. I will not go into details, most of you already know that those no-coding small RNAs are really connected with all the epigenetic marks, are really the transmitter of information between what's happening in the chromatin and what's happening on genes and their expression. It's quite a complicated cartoon, but you can see quite clearly here that there's a close relation between what's happening around the chromosome and gene expression, with the small RNAs acting as mediators. And of course, now we discovered quite recently that DNA methylation is really modulated by several types of small interfering RNAs. So now things are becoming a bit clearer. That's not really exactly what's happening from this cartoon, but DNA methylation and the presence of